Okay, last big lecture of the unit. We have a little bitty one tomorrow, but this lecture is going to focus now on the third way to determine a rate law, and that's using graphical methods of integrated rate laws. Don't let all those fancy words scare you, because it's really nothing to be scared of. Integrated rate laws. So in order to do this, you're going to need a graphing calculator. You're going to be expected to use a graphing calculator, not on tomorrow's test, not on tomorrow's quiz, but on this group quiz and this test. We're teaching you how to graph to determine order, which you can try it by hand like I did in high school, doing linear regression by hand. These problems took literally 3.5 hours to do. I would sit at the Trinity Library, because I went to school across the street, Incarnate Word High School, and I'd sit at the Trinity Library, and we'd look at all the boys. We had our uniforms on, watching the boys while we were doing these problems that took forever. And maybe they wouldn't have taken as long if we weren't being so off task and staring at boys, college boys. Yeah, that's what I did for fun in high school. Sad days. Did integrated rate law problems in the Trinity University Library. But anyway, back to the point. So the calculator is an integral part of what we're doing, and it's going to make your life a lot easier than mine was, but that's what technology is all about. So starting with this is, again, the last and final way we're going to use to determine rate law. Before we can get into the graphing part, I want to introduce you to the actual integrated rate laws. So here, do we all agree that this is a zero-order rate law? All right. Someone out there went and decided to integrate this, like in calculus, from time 0 to time t, and when they did, they came out with the following equation that you do need to memorize. I'm going to write memorize. I don't want you to freak out, though, because I'm going to show you a trick when it comes to memorizing, because you have the other two. This is the only one you don't have. And so when you integrate from time 0 to time t, concentration minus original concentration is equal to negative kt. A minus A naught is equal to negative kt. This is what we call an integrated rate law. Someone integrated this from time 0 to time t, and this is what they came up with. What this is used for? It's used for a lot of things. It could be used to find the concentration after a certain time has passed and you know the original concentration. So you can use plug and chug methods to find any of those variables, and it's pretty commonly used for that. Another thing we can do is linearize this equation and graph it to prove zero order. So to linearize this, all I need to do is I'm going to swing that minus A naught to the other side of the equation. And so I'm going to get A is equal to negative kt plus A naught. A naught's a constant. A naught doesn't change. That's the original concentration. And in a line, that y-intercept is constant. So what we've done here is we've made y is equal to mx plus b. So we have made ourselves a little line. So looking at the linearization of this, what would I plot on the x-axis to prove that this were a zero order? Look at the x. What would you plot? Time. And on the y-axis, what would you put? Concentration. So if you plot time and concentration and you get a straight line, you're proving it's a zero-order reaction. Now notice, this is a negative slope, and that is true. And one thing I want you to look at is this. Part of a rate law is determining order and rate constant. So once you graph this, you can take the absolute value of the slope to give you the k. Just remember, you can never have a negative k. K has to be positive. So if the slope is positive, you leave it positive. If the slope is negative, you make it positive. So the absolute value of the slope then is going to always be your rate constant. So once you graph all the ways you're going to learn, you can then use the slope of whatever line is more straight, and then you'll know the whole rate law. So is everybody good so far with zero order? All right, we're going to, thank you. Go ahead and skip one more. We're going to skip the half-life stuff. I'm going to end up going back to it. But right now, I just want to focus on first order. So again, someone integrated a first order reaction from time 0 to time t. And when they did, they got the following equation. They got ln of A minus ln of A naught equal to negative KT. Good news is this is on your AP sheet. You do not need to memorize this. However, it is not labeled first order. So you need to know it's a first order. It's just not labeled as such. Okay? If I'm to linearize this, again, I would pull across that minus ln of A naught. So y would be equal to mx plus b. What would I plot to prove a first order? What goes on the x? Time. What goes on the y? ln of concentration. This again is going to have a negative slope. So the K then of the first order reaction would be the absolute value of the slope. And in your calculator it's A, it's not M. We know that, right? Good so far? All right, go 2 forward. Okay, so let's do our second order, which is our final order. When this is integrated from time 0 to time t, they get the equation of 1 over A minus 1 over A naught is equal to, this time it's positive KT. Positive KT. So when we linearize this, 1 over A is equal to KT plus 1 over A naught, y mx plus b. Again, we're going to put time on the x, but now what are we putting on the y? 1 over concentration. And this time, our slope is positive. That is a characteristic that will help you answer some questions. It's the only of the 3 orders that we typically graph that has the positive slope. So it's an identifying thing, so you got to know that. And this K then is equal, and you can say absolute value again, it doesn't matter. If you just remember that, you'll be good to go. So on the sideboard, I have what's on your AP sheet. This one is on the AP sheet as well. If you look, you have the natural log, and then you have the 1 over. They're not labeled 1 and 2. You just need to know this is first order, this is second order. The way you remember 0, take out the natural log. And that one goes up here. Okay? It's not on the sheet, but you really don't have to memorize it, because that is it right there. Okay? So those are the 3 integrated rate laws that you will either have to do problems with or you'll have to graph from. So in synopsis, go ahead and go one more screen. One more? Okay. Summary. And you have already pre-typed 3 summary blocks. Do you see them where it has 3 different graphs? And I'm not going to go through all that. That's for your reference, but I'm going to give you a little hint here. If this is a 0 order, this is 1, and this is 2, let's review what we're going to graph. What are we going to put on the x-axis for all of these? Time. All right. What are we going to put on a 0 order? Concentration. Concentration starts with a C. What are we going to put on the first order? ln of concentration starts with an L. What are we going to put on the last one? 1 over, or reciprocal, starts with an R. So it's clear to see what the graphing is. See what I did there? See what I did there? There's also this product you can buy called CLR, calcium lime rust. It's in a gray bottle, and it looks like a stop sign on the, a red-green. It looks like a stoplight. Red, yellow, green. I don't know. I think clear is a lot easier. So what about the slopes? What's the slope of a 0 order? Negative. First, this one, positive. Okay? So they ask a lot of questions. Are you ever going to have to sit there and actually graph this on the AP? No. Through the process of graphing, you are learning these characteristics, and you know it a lot better than there's some people out there, because students don't have calculators or they themselves aren't comfortable teaching students with calculators. They're just like, memorize this, and they never graph it, and they don't have a working understanding of it. So the fact that you're doing it, this is going to be like a welcome problem for you. You're going to be like, oh, I know that, and so it's a good thing for you to graph them. All right. So what I want to do is, let me do this one. Are you okay over here? Okay. I don't know where I want to go. I want to go to the half-life of a zero order, which is the second slide. I'm not going to cover a ton about half-lives, but I do want you to kind of have a working knowledge of it, and we'll talk about an equation that is on the sheet that you need to know what it's for. So I'm only going to talk about zero and first order to give you a point of comparison. First thing I need to know is, what is a half-life? I meant to do this. Time required for the initial concentration to fall to half its value. So when I say half-life, what is the first thing that usually pops into your head? Huh? Carbon. Why are you saying that? What grouping of elements are we talking about there? Why carbon? Half-life is right. Carbon dating. What's special about carbon dating? Radioactive. When we talk about half-lives, most people's heads go to radioactive stuff, okay? But I just want you to understand that half-life, every reaction has a half-life. It's literally the time it takes half of it to get to product, half reactant to turn to products. So what I'm going to do is derive the half-life equation. I'm going to make one half-life pass in the integrated rate law and have an equation represent that. So the integrated rate law for first order was A minus A naught is equal to negative KT. So what am I going to, when one half-life passes, what's the relationship between A naught and A? A is equal to what? Half of the original, right? Does everyone get that? When one half-life passes, sounds like a gunshot. Made me like drop to the floor. It scared me. When half-life passes, half of the original goes away. Is everyone good with that? So what I'm going to do is wherever I see A, I'm going to plug in A naught over 2. So A naught over 2, and I'm just leaving off the brackets for ease, not because it's not concentration anymore, but because that happened after one half-life, I'm going to call that T1 half. So this is the integrated rate law after one half-life has passed. We've got to clean this up. That looks really ugly. So isn't 1A 2 over 2, right? So what does that leave me with? Negative A naught over 2 is equal to negative K T1 half. So I'm trying to make this a half-life equation, so I'm going to isolate T1 half by dividing both sides by negative K, and so I get concentration of A naught over 2K. So why are we going through all this? We really don't have to. I'm just trying to make a point. If you were asked to find the half-life of a zero-order reaction, you'd plug in the original concentration, you'd plug in K, and that would give you the half-life. Okay? I don't expect you to memorize this, because what if I asked you to find the half-life given that same information using that one? What could you do without having to memorize that one? You already know this one. You have, if I were to ask you a problem, you would have K and you would have original concentration. Plug it in, but what would you put here? Put half of the original into that slot. So when you plug in if I said the original concentration was 100, you could plug in 50 there, right? And then you could just solve. And that would be the best way to do it, okay? Because mathematically, once you divide it, you've already done all this mess. But I want to make a point. So just take a look at this for a second. And now I want to go ahead 2 slides. Okay, we're going to now do the first order one. This is important. This equation is on your AP sheet, so I want you to know where it comes from. So I'm deriving it so you know where it comes from. The half-life first orders are super important because all first order reactions, let me rephrase that, all radioactive reactions are first order. All radioactive reactions are first order. So when we talk about half-life, it's hugely important in this genre right here. So first order, what was the integrated rate law? Natural log A minus natural log A naught negative KT. So again, if I want to derive the half-life equation, A naught over 2 is equal to my A. So I'm going to plug that in where I see A. ln of A naught over 2 minus ln of A naught is equal to negative KT. I'm going to put a little 1/2 there because I'm at a half-life. Okay, so cleaning that up. When I subtract logs, what am I really doing? Whoa, I'm really dividing, right? So I could say natural log of A naught over 2 all divided by A naught, and that's the same thing. And that's going to be equal to negative KT 1/2. So I can clean this fraction up even more by getting rid of those A's. So I have the ln of then numerical 1/2 is equal to KT 1/2. What's the natural log of 1/2? You have calculators. I have a calculator right here I could use too, but I'm not going to. Negative 0.693. That's the natural log of 1/2, and that's equal to KT 1/2. So if I divide each side, whoa, it should be, I lost a negative here. Like, what happened? It should be negative KT 1/2. So if I divide both sides by negative K, I get 0.693 over K is equal to T 1/2. And that is my half-life equation. This is on the AP sheet. So you're going to potentially use it. It's an important reaction. It's an important equation. So what's the big difference? And here was the point I was trying to make. What's the big difference between that zero order and now this first order half-life equation? Exactly. You see how initial concentration is not in here? And think about what you know about radioactive substances. Don't they have a set half-life? Like, in carbon dating, isn't it a set amount of, regardless if it's a tree or a little bitty rock, doesn't carbon decay the same half-life? Okay? And that's because it's first order. It does not depend on initial concentration like that other one did. Okay? Again, this is on the sheet. You do not need to memorize it. Okay? So now let's go to, I'm going to go forward quite a bit to work some problems. I'm not doing all of these because I think they're really easy. They're just choosing the right integrated rate law and plugging stuff in. So take a look at number 9. It says the decomposition of H2O2 to water and oxygen follows first order kinetics with a rate constant of a certain thing in a particular temperature. Calculate the hydrogen peroxide after 10 minutes if its initial concentration is 0.2. This is literally just plugging and chugging to find the concentration of H2O2. First order kinetics, so we go to the first order rate law, bam, ln of A minus ln of A naught is equal to negative KT. Just a game of units. You just really need to watch your units. So I'm solving for my natural log of A minus natural log, my original concentration they gave me as 0.200 molar equals, they gave me a rate constant of negative, thanks, Chloe, 0.0410 1 over minutes. That's per minute. Now, this is where you have to be careful. You have to put the time in. Based on that K, what does your time have to be in? Minutes, and they were nice here. They gave us 10 minutes. All right, so we're going to pretend that 10 minutes is 2 sig figs. The little dot there. I can't stand 1 sig fig answers. So using that information, let's solve for this A. Well, this A, I should say. So it's easier to solve than it seems. You're going to multiply those two, right? And then you're going to add 0.2, natural log of 0.2 to both sides. What I want you to give me, though, is what is the natural log of the A equal to before you fully solve for it. I want a number here to make sure everybody. What'd you get? That kind of sounds familiar. Anyone else? Not sure, though. Negative 2.02? Negative 2.02. So how do we solve for the A? What do we do? E up, e to the, that gets rid of this. So A is equal e to the, which is second natural log on the calculator, second e, to the negative 2.02. So what does A come out to be? Which I really should change this to the actual name of the reactant, which is hydrogen peroxide. Say it again, Warner. 0.13 molar. Someone else get that? Okay. So these are literally, like I said, they're just plug and chug. I'm going to go through a couple just to make some points here. So go to the next slide, please. In this one, you're supposed to calculate the rate constant, and it is first order kinetics. So it's that same equation. But here's the thing about this. I'm not doing it. I just want to talk about the units. Do not sit there and use that crazy integrated rate law to find the units of the K. Do the shortcut, because you have everything you need in here to do the shortcut. I can find the units right now, which is what we're going to do. It is, we know, first order. So 1 over, what is our unit of time? Minutes. And then our thing is in molarity, right? What's 1 less than 1? 0. So what are my units? 1 over minutes. So utilize that shortcut in times like this, because using the integrated rate law to figure it out with all the natural logs and the reciprocals and all that kind of stuff gets way too confusing. Okay? Go ahead and go one ahead. Let's just talk about this. How long would it take for half of the H2O2 to decompose? So I'm not going to go back. Y'all tell me, what was the information they gave us? What was our original? 0.200. And then that was equal to the H2O2 naught. And then what was the K they gave us? 0.0410. And the units on that was 1 per. All right. Now, here's the deal. There's 2 ways to do this. Because this is a first order, you have a half-life equation that you can use on the sheet in front of your faces. And that half-life equation is what? 0.693 over K. So all you have to do is plug that K in to solve. And that would give you a half-life in minutes. Okay, what did you get for that? So 16.9 minutes, right? Let's say you're having a bad day and you totally forget that the half-life reaction exists. You're like, I'm going to go to a first order integrated rate law. And so you're going to have ln of H2O2 minus ln of H2O2 naught equals negative KT. What's a different way you could do it? Do I know the, yeah, you can plug in the original, which is 0.2 here. You can plug in then 0.1 there. Because it's first order, though, you could actually do 150 or 2 in 1. It doesn't matter if it's first order. That's the only time it doesn't matter. But anyway, you can plug those in, plug the K in, and solve, and you'll get the same answer. All right? Okay, time for the graphing stuff. Yeah, we're not going to do any more of those problems. You can go. I'm only going to switch one more. Okay. Go to number 14 and 15. We're doing 14 together. If you know how to do this, just quietly sit and do your own thing. If you don't know, I'm going to, on this calculator up here, I'm going to turn the lights off a little bit. Not a lot, because you have to see your own calculators. And show you how to do this. The synopsis of what we're doing. You're going to graph all three things, 0, 1, and 2, do linear regression. Whichever one, how do we know which is the best when we do linear regression? R squared. I want you to do R squared just so we get the negatives out of play. Whichever R squared is closest to 1. So the best way is to organize your data in a way that makes it fast. So my suggestion is to do, in your list, in your stat edit, you're going to put time in L1. You're going to put concentration in L2. I'm going to teach you guys how to do something called a batch transformation. I'm going to take all the concentrations in L2 and convert them to, we'll do 1 over concentration in natural log of concentration in L3, and then we'll do what in L4? Yep, and we'll do 1 over concentration in L4. So once you get those batch transformations done, you've got all your data in your list. It's really quick to do linear regression. For 0 order, what would we be for 0 order graphing? What two lists? We do L1 and L2. For a first order, we would do linear regression on L1 and L3. And then to prove a second order, we'd be doing linear regression on L1 and L4. So that's what I'm going to take you through. And again, if you know what you're doing, cool. You can quietly work on it, but be ready to answer questions as I ask them. So first thing you want to do in your calculator, since we haven't done this in a while, is to turn on your diagnostics. So if you've done any memory clearing recently, you're going to have to do this. So to do this, you go to hit the second and then the mem button. Not memory, dang it. Second catalog. I'm thinking of clearing list. Second catalog. Second catalog. Why isn't this working? Let me log it. Let me close this and reopen it. It's not playing ball with me right now. Of course, when I'm videoing, this is what happens. Oh my goodness. I think my computer's being crazy. Where did it go? Sorry, those of you at home. I'd sing to you, but I don't think you'd want to hear me. Oh, I think it's back there. Nope. Where is it? Where is it? Let me quit it, and let me try it again. Maybe it's just weird because it needs to be reopened. Oh, y'all, I'm upset. While you're waiting for me, put in L1 your time. So go to Stat, Edit, and put in your time. And then in L2, go ahead and type your concentration. Why did this do this to me? Maybe this just doesn't work for some reason. When I'm videoing, it could be. There it is. Yes. Okay. So I've got to turn on my diagnostics. No, second. So I forgot to tell you diagnostics, didn't I? Did y'all figure it out? You scroll down to your diagnostics, and you hit enter, enter, and that'll turn them on. Diagnostic on, enter, enter. All right, stat. Now I've got to catch up with y'all. Sorry. So I'm going to enter my time in L1. I just really want people at home to be able to see this. That's why. 5,000, 7,000, 11,000, 15,000. So go to L2. 1.5, how many zeros is that? I could be faster if I didn't type the zeros in. No, negative was right. So 0.0014, 0.00127, 0.00118, 0.00103. This is 3 zeros, 0.0009. Okay, is everybody with me? Yeah, because I've been really slow. So to do a batch transformation, what you do is you take your cursor up to the very top of L3 to where you're making L3 black. Okay? Now, we're going to put into that list 1 over concentration, right? Where is concentration again? In what list? It's in L2, right? So we're going to go, oh, we're doing natural log. Yeah, y'all need to stop me from my craziness. Sorry, people at home. First order is natural log, and that's what I want to put in this one. So I'm going to hit the natural log button. Do you see how it shows up right there? And then we're going to type in L2, which is found as a second function above the number 2. Second number 2 will give you ln of 2. And what this is saying is that in L3, I will put natural log of L2. Hit enter, and it puts everything from that list into L3. The natural log of everything. You okay, Arjun? You have a funny look on your face. So what do we want to put in L4? 1 over. So I'm going to do, again, to the tippy top of the list. You have to blacken L4. If you were to leave it here, it would do it, but it would only do it for 1 data point, and that would kind of stink. You want them for all. So you would do 1 divided by second number 2, L2, or you need to do L2 to the negative 1. Both of them work. And you hit enter, and then you've got that. That's a bad number. Bad number. Let's get off of that. Okay. So now I've got my data set up, and now I can just quickly run through all my linear regressions. Here's the deal. Because this is so quick, I need verification that you've done all 3 orders. So my requirement is for each of them, you write down the slope and the R-squared for all 3. That's the work I'm checking. So don't be like, oh, I'm just going to assume number 1 is good because it's a 1.0 and you're done. I want you to do all 3. So to do linear regression, we do stat, scroll over to calc, hit number 4. Now, do any of you have an older operating system where all you see is linreg written? Okay. You do? But you know how to do it? Okay, got it. So this one, you would change your list. This looks good to me. It's got L1 and X and L2 and Y. So this is proving 0 order. So I would have you write down for 0 order. I'm not writing this down since I'm not at the board. You would write down -4 times 10 to the negative A is the A, it's the slope, and I want you to write down 0.994469. Just write down quite a few numbers on those R-squareds. All right. So that's your proof of 0 order. Did y'all get these? Okay. I'm just making sure my numbers match. Everyone matches? Okay, now we're going to do first order, the second one, stat, calc, linear regression. For first order, we do L1 comma what? What do I put in the Y? L3, correct. Enter, 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 enter. Wow, that one looks really good, 0.99989. Again, I'm looking for the number with the R-squared closest to 1. So write down your slope. Be careful. A lot of students forget this e to the -5. They get caught up in these numbers right here and forget that. This is an exponent. So negative 3.41 times 10 to the negative fifth with an R of 0.999896. Okay, now let's graph the last one, stat, calc, linear regression. This time we're doing L1 and, hello, L4, enter, 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 enter. There you go. Not as good as the other one, but write it down. That's how I'm grading you. There's going to be 6 things I'm looking for, 2 from each. Okay, so we know that's not the right one. So just for teaching purposes, I'm going to go back up to the correct relationship so I have it in front of me. So what order is it? What order is it? First order, which is the L3 being graphed. I'm going to go ahead and drag this puppy over. Oh, I guess I can't, can I? Okay. That'll work. And I'm going to go ahead and show you how you need to format your answers. So you should have, at this point, written down the slope and the R squared for the 3 different relationships. That should be on your paper. Now what you're going to write, because the question asks for the order, so we know it is first order. You have to write your rate law and the K. So right now your rate law, based on not specific to the K yet, rate is equal to K times, what was, I don't have the name of the reactant, I can't see it, what was it? On the top of the column? N2O5 raised to the first. That is our rate law. We need to find K. What was K again? Absolute value of the slope. So my slope is 3, the absolute value of it is 3.41. I'm looking at the calculator for those of you at home. I'm looking at A, 3.41 times 10 to the negative fifth. Units on K, this is the real reason I taught you the shortcut. There's no equation to solve for units, so you have to know the shortcut. 1 over, what's the unit of time in the table? Seconds. And then it's first order, right? So molarity, 1 less than 1 is 0. So it would be molarity to the 0. So these are the units. So this is what I'd expect you to do. Okay? All right. So I want, on your own, to do number 2. I'm going to write the answer down on the video for the people at home, but I'm not going to show it to y'all. You guys keep working, and I will walk around and help you once I write this down. So those of you at home, it is this order. Whoa, can't see it. It is this order, and the K is point. And that's your K. So the rate law would be rate is equal to K times. What's the substance in number 2? NO2. NO2 squared. There you go. That is the answer for those of you at home. Have a good day.